Now let's put Lamport's clock to work for implementing a distributed mutual exclusion lock algorithm. And it is going to be very similar to the car sharing example that I showed you before. And also you will notice that we've talked about locks in a shared memory multiprocessor where we have shared memory to implement the lock. But now in a distributed system, we don't have shared memory and we have to implement a mutual exclusion lock using Lamport's logical clock. So essentially what is going to happen is that any process that needs to acquire this lock is going to send a message to all the other processes. And of course, the intent to get a lock may emanate simultaneously from several processes. That's perfectly feasible. So the algorithm is as follows. Every process has a data structure, a queue data structure, and this is the queue that is associated with process P1. This is the queue that is associated with process P2, and this is the queue that is associated with process Pn. Every process has its own private queue. And the private queue is ordered by the happened before relationship that we've discussed so far. So requests for a lock are going to be time-stamped, and the protocol is as follows. To request a lock, what a process is going to do is send a message to all the other processes that I want this lock and my timestamp is such and so. So it is going to associate the local timestamp that it has from its counter, which is its logical timestamp. It's going to associate that timestamp as the request time for the lock and send the message to all its peers. And all the peers, what they're going to do? Well, two things. One is they're going to stick that request into their local queue. When a request comes in from process Pn, P1 puts it into its queue, appropriate place in the queue, because it is ordered by the timestamp, the smallest timestamp being the highest priority request pending. So it puts it in its queue. And the second thing it does is every process, when it gets a request, puts it in its queue and then acknowledges the request to its peers. So let's look at process P2 here. When P2 generated its request at timestamp 10, what it did was to first put its request in its local queue, and then it sends a message to its peers. And these guys, when they get the request, they look at their own local queue and say, well, there is a request pending in my queue, which is a timestamp of 5, and this request that I just got from P2 has a timestamp of 10, so I'm going to order that behind the previous request. I put it over here, I put it over here, and once I do that, I'm going to acknowledge this request by sending a message back to P2. And similarly, this guy sends an acknowledgement back to P2. So that's how the protocol works. Every request is sent to all the other processors, and every process, when it receives a request, it puts it ordered by Lamport's clock in its own local queue, and then acknowledges the request with an ACK message. Now what happens when there's a tie? Well, when we have a tie, we break the tie by giving priority to the process that has a lower process ID. So that's how this algorithm works. So that every process can unambiguously make a decision as to where to place an incoming request in the queue. So an example of the state of the queue is as shown. The thing that should jump out at you immediately is that the state of the queue is not the same in all the processes. So for instance, process 1's queue contains its request that it generated at time 2, but I don't see it yet in the other queues. Is this possible that the queues can be inconsistent with one another? Of course it is possible. The reason it is possible is because a process, when it generates a request, puts it in its queue and then sends a message out. This message is going to take some time to reach the other nodes in the distributed system. So this is sent the message, and after it sent the message, it got requests from other processes and it has put it in its queue. And it is possible that this message, all the messages may not take the same amount of time to traverse the network. We have no idea what's going on in the network. And therefore, it so happens that P1's message is still in transit, whereas the request messages from P2 and Pn have already made it everywhere and it is in the queues of all the processes. But P1's message, unfortunately, it's taking a slow route through the network and it is still in transit. And in fact, P1 has subsequently received P2's and Pn's message and put them into its local queue It is just that P1's message hasn't reached its peers yet. And that's how you get the situation. So the whole purpose of this exercise is to unambiguously get the mutual exclusion lock for some process that is competing for it simultaneously. Now, how does the process know that it has the lock? So I have to make a decision that I have the lock. How do I make the decision? Two things have to be true for me to think that I have gotten the lock. So the first thing is that my request has to be at the top of the queue. So now you see the messages that I talked about, that is P1's message to P2 and Pn not having reached the destination. Eventually they've reached the destination and they have acknowledged it. And as a result of that, the queues are consistent now. P1's request is at the top, and it also has received acknowledgements from everybody else. So the way you can make a decision that you have the lock unambiguously in the entire distributed system, two conditions. First thing, my request is at the top of the queue. The second thing is I've received acknowledgements from all the other nodes in the system. In this case, all the other nodes were not requesting this lock, so they've sent me acknowledgements, and I've received all the acknowledgements, and there is no other request that is ahead of me. I've also received lock requests from P2 and Pn, and they are later than mine, and that's how they've been ordered in the queue. So the two conditions I'm going to look for to make a decision locally that I have the lock is my request is at the top of the queue, and I've either received acknowledgements from all the other nodes in the system, if nobody else is competing for the lock at the same time, or all the requests that I've gotten so far are later than my own lock request. Let's say that I haven't received the acknowledgement for my request from Q2 and Qn. Can I go ahead and assume I have the lock? Yes, I can. Why? Because even though these guys have not sent me the acknowledgements yet, it's coming. It's slowly coming. But I've received lock requests from them with timestamps 5 and 10 respectively. Therefore, I can make an unambiguous decision that my lock request precedes all the other lock requests at this point of time. And I can go ahead and get the lock. I'm sure you've figured it out already, but since we are following Lamport's clock in implementing this mutual exclusion lock algorithm, the ACK message for a particular lock request is going to have a later timestamp than the timestamp associated with the request itself. So you can see that Lamport's logical clock, with the addition of a way of deriving a total order from the partial orders given by the Lamport's clock, allows us to unambiguously make a decision locally based on the state of my local queue as to whether I have the lock or not. Now let's talk about how I go about releasing the lock. So if I have the lock, I've used it for a while, and now I'm ready to say, well, I'm done with the lock, I can release it. What do? Well, I'm going to send an unlock message to all the other guys. The first thing that I do, of course, is get rid of the entry that I have in my queue. Because I'm done with the lock, I can remove it from my queue. Once I remove it from my queue, I'm going to send an unlock message to everybody else. So the state of the queue indicates that the unlock message hasn't reached yet. It is in transit. It is going to eventually reach these guys. And when the peers receive the unlock message, they're going to basically remove the entry, the corresponding entry from the respective queues. So P1's turn with using the lock is complete now. It has done its lock and it has done its unlock. And now other processes in the system, if they're competing for the same lock, can use the same decision-making process to figure out whether they are the winners for getting the lock next and using it and entering the respective critical sections.